There we go. Okay, so everyone should see the screen now. I titled this talk Modeling, Not Programming, and you'll see that a lot of it has to do with decisions when you're doing optimization between approaches that use modeling and approaches that are more programming based. And you also see why I call this a modern approach, sort of. And let me start out, if you may have been curious, like, where does the optimization, where's that term come from in operations research? You can look it up in the dictionary, and it'll say something like the action or process of making the best of something. Okay, but if you look closely, it says rare before the mid-20th century, and if you look down to an example of that term being used, then it'll say minimization of costs or maximization of profits, and that's really what the sort of optimization I have in mind. The same thing happens if you Google it. If you Google optimization, it'll give you some general thing about making the best or most effective use of a situation or resource. But the first thing that comes up is the page on mathematical optimization in Wikipedia. And in fact, if you type optimization into Wikipedia, it redirects to mathematical optimization, which is what I have in mind. And of course, they give like 3 definitions on the Wikipedia page, but for example, consists of maximizing or minimizing a real function by systematically choosing input values and computing the value and so forth. That's more or less what I have in mind. So let me say specifically what to me is optimization and operations research. And you're given this need to make many interrelated decisions recurring. So all the time, you have to keep making these decisions every day or every week. And you want to consistently make highly desirable choices. I mean, I could say the best choices, but it doesn't have to be absolutely the best. And you want to apply ideas for mathematical optimization, ways of describing problems, which we call formulations, and ways of solving them that we call algorithms. And when this is done in practice, what's it look like? Well, there are very large numbers of decision variables, at least thousands. And an objective function, some mathematical function to be minimized or maximized. There are various kinds of constraints. And then you solve it many times with different data. And you can't really predict what kind of solution you're going to get as the data change. You really have to solve it every time to find out. And finally, to solve it, you have to take these computational steps. And the algorithms are not very simple. You don't know how many steps you're going to have to take. There's a lot of work, special work you're going to have to do to get a good solution. Okay? And so let me start with a little history here. The first time that people actually described a way of doing this optimization, this practical optimization in a way that would actually get answers was in this paper back from 1953. And with this mysterious title about alternate algorithm for revised simplex method. And the 2 authors of this paper are George Danzig and William Orchard Hayes. And I like to bring it up because I knew both of them. And in fact, both of them were very important in my getting involved in optimization, okay? But not in 1953. Okay? Much later than this, it was a few years after I got my undergraduate degree. I took a job working for a research center in Cambridge, where they had hired Orchard Hayes to build a new linear programming system. And the thing was that they were all experts in statistics, really, and they were having a hard time writing any documentation for it that didn't sound like statistics. So the idea was, well, I had a math degree, they could hire me and they could give me Orchard Hayes' book and I could read it and figure out what they were supposed to do. And so I was very fortunate that this is how I learned about linear programming, because this was like really detailed computational stuff, whereas all the textbooks back then told you how to solve them by hand. And this really told you how to solve them by computer, which was quite a different thing. And so I wrote some documentation, and I did a lot of other things there. And some of us got together and started thinking about how we thought linear programming systems should look, or optimization systems. And actually we thought that, well, Orchard Hayes had been a trailblazer back in 1953. By the time I had this job, we thought of him as sort of the old guard, you know, and like we were thinking of what's a new and better way to do optimization. and how should it be done with today's systems? And that led to this paper called A Modern Approach to Computer Systems for Linear Programming. So two of us wrote this paper and suggested things, how we thought things should proceed. Okay? And so that's where modern approach comes from in my title. And I'm going to come back to where things went after that. Okay? But that's how I get started. So the outline of this talk is that I'm going to talk about certain aspects of the modern approach in 3 steps. And in each step, there's going to be a programming approach and a not programming approach. Okay? A modeling approach and a programming approach. And the first one's just going to be about how should you do optimization. And then if you take a modeling approach, how should you do it? And then if you choose a modeling language, what kind of modeling language should you use? So in each case, it'll turn out one approach is more programming based than the other. And then I'll discuss more. I'll say more about my history as I go along. Come back to that. And then at the end, I'll say something about the range of AMPL users, and I'll do 3 quick case studies. So when you get started on modeling, not programming, what about optimization in general? How do you get from having a problem to getting a solution? And so you have a problem statement here with a bunch of these things that I mentioned, and you want to get to this algorithm and make it work. Well, there are 2 approaches that I think basically that there's what I call the method-based and model-based approach. And in order to describe those, I'll give you an example. So in this example, which was an actual application, but it's easy to understand, there was a meeting of employees of this firm from around the world, and they had various categories of employees, like where they were and what their title was and so forth, and a number of project groups that they wanted to divide them into. So they wanted to put each employee into a group. They wanted the groups to have about the same size, but what made it difficult was they wanted the groups to be as varied as possible. So the idea was that there shouldn't be too many people from any one place in each group, not too many people from any one department in each group, et cetera, et cetera. They should all be mixed up as much as possible. So if that's the problem, what are the 2 approaches? Well, the method-based approach is the programming approach. Program an algorithm to build a balanced assignment. So here's an example of an algorithm. You start with all the groups empty, you make a list of all the people, and you take them one at a time, and you decide what group to put each one in. And you put them in the group that will create so that the least sameness is created in that group. So you have to have some way of measuring sameness, of course, which I'll come to. But you just do this. You put them one at a time. It's called a greedy algorithm. When you're done, you get a pretty balanced assignment. You can even write a little pseudocode for it here. And what's the sameness? Well, you can say the sameness of 2 people is the number of characteristics they're the same in. So if you're both from New York and you're both vice presidents, but you're different in other ways, then your sameness is 2. And the sameness of a group, you take all pairs of people, you compute their sameness, and you add them up. Okay? And then there's all sorts of study about how to refine this and make it better. But since I'm not giving a whole workshop on this, I'm not going to say what those are. Just want to mention that like this is only the very simplest way of doing this. So what's the model-based approach? Well, you formulate a minimal sameness model. Okay? You don't even think about algorithms right away. You say, I just want to formulate a model of minimal sameness. So I define some decision variables. I can say Xij is my variable. It's 1 if person I is assigned to group J and 0 otherwise. And you make some sort of constraints. You write down that express what assignments are allowed. And then you formulate the sameness as an objective to be minimized. We're going to minimize total sameness among all possible ways of assigning these variables that satisfy these constraints. Now I've got a model, a description of what I want by minimal sameness. But of course, I still have to solve the problem, right? And so the second part of model-based approach is that you send your model to an off-the-shelf solver. So you take some software that somebody else has been working on for years, and you send your problem to that. And this solver accepts these things I've described: variables, constraints, objectives of some general mathematical kind. It doesn't know you're doing an assignment problem or which kind of constraints you have. It just knows that it fits in the kind of math that it can do. And you send it to this general one, and it sends you back a solution. So this combination of a formulated model and an off-the-shelf solver is the model-based approach. And just to prove that that the model-based formulation, you can really write it down in math. Well, you have a set of people and a set of categories and some types, the number of groups and the lower and upper limit on number of people in the group. You define the sameness of any two people by adding up the number of types in which they're the same. And then here's the variables from before. And I can write the objective. Minimal sameness is this expression. And, I don't have enough time to go through and explain every expression in every model. So what I'm going to sort of rush through these things. And so I want you to know that, like, I'm not expecting that all this is so simple that you can look at it for 2 seconds and understand it. But I just want to give you an idea for what I'm talking about. So you see, I've reduced it to a mathematical expression. There's some pairs of variables multiplied, so it's a quadratic objective. And then there's 2 classes of constraints. And the first one says for each person, the number of groups they're in is 1. And the other one says for each group, the number of people in them is between the min and the max. So I've reduced it to a mathematical formulation. And now I can send it to one of those solvers. Okay? So now if this were really my problem, then you could have a pretty good argument about which way you want to go, with method-based or model-based. But I've really left out the key thing about optimization, which is that there are always complications. It's never that simple. And that's what happens with this, and it's what happened to me. Okay. Well, the client has a trouble with total sameness. The total sameness could be 366. And like, how do they know if that's small or large? It seems like this very sort of weird quantity. And a friend of mine suggested using total variation instead. So what you do is you take the number of people, the most people from New York in any group, and the least people from New York in any group, and you take the difference. And that's the variation in New Yorkers. And then you take the same for people from Boston and people who are vice presidents and so forth. And you add up all those variations, and that's the total variation. If you have 17 different categories and the minimum variation is 16, you know you're doing pretty well. So we use that instead. And then they said, oh, but also we have these special requirements. We forgot to tell you. We have to worry about isolation. No group can have exactly 1 woman, they said. And they said that every group person must have somebody else in their group from the same location and of equal or adjacent rank. I mean, you couldn't make this up, right? This is something they thought would be sure that they have at least 1 person to talk to. And so we're supposed to put this in the model. So what happens when you try to do that? Okay. Oh, I should say there's also some other things I won't even mention. And well, in the method-based approach, you have to redo the method. And the thing is that total variation is not so suitable to that greedy approach. And the isolation constraints are hard to maintain as you start adding people to groups. And so it turns out that the method becomes more complicated. You really have to think it through again to see how you're going to come up with a bunch of groups that satisfy these requirements and then minimize this other objective here. And then you have to rewrite the program. Well, if you came up with a different method here, that you have to redo it. And even a small change can cause your method to have all sorts of new features in order to take advantage of it. Okay? And so you're forever, every time the client says, oh, but I forgot, or why don't you try this? You have to go back to your program and redo it. Okay? And this is where model-based comes into its own, because to do this with model-based, I replace the objective with a new objective. I have to change the math some. And I add some new constraints for the isolation that might take some thought. But once I'm done that, I send it back to the solver. As a bonus, it turns out the solver actually does better with this total variation objective. It's actually easier. And so all I have to do is redo some math, and I don't have to worry about redoing any program at all. The solver is the same solver, okay, that I took off the shelf before. Okay, there's no programming redone. I just have to worry about the formulation. Okay? So just to show you what happens there quickly, I have to add some more variables for the least and most people of each category that are in each group, and then some constraints that sort of relate the least and most to the number of people in each group, and then I just minimize the sum for each type of person of the maximum in each group minus the minimum. Okay, and that's my new objective, and now it's linear. And now for women in a group, it's more complicated, but let me just say that you have to have have to figure out the set of women, and you add a constraint that says that for each person, for each group, the number of women is either 0 or it's greater or equal to 2. And now my solver doesn't actually know about constraints like this. So what I do is I define a variable that tells me if there's a woman in a group or not. And then I say if there are no women, then the total number of women in the group is 0. And if the variable says there are women, then it's greater or equal to 2. And my solver will take this directly, but if it won't, then I can actually make it into just plain old algebra. Okay, so it's just by way of showing what goes on. But once I'm done, I've got my formulation. Okay, and eventually I'll come back and show this again in AMPL. But to move on, so there are various uses for method-based. Just to finish up this topic. Okay, it's great for unusual problems that are really hard to formulate mathematically. They have black boxes or weird things, not suitable for solvers. There are still some problems like that. Cases where you have a simple problem that you just want to solve a million times. So you really want to get the absolutely fastest solve by programming it yourself. And certain very large applications, like if you're Google Maps and you have to find the shortest route like a zillion times a second, then you can afford to have an entire department of programmers that do nothing but work on your algorithm. Okay, but model-based is great for lots of things. It adapts to complications in lots of kinds of problems. It focuses on models, which is what modelers want to do, the people who actually own the problem. And it leverages years of solver improvement. So when you send something to a solver, people have been working on that and done all these clever things, and you get that benefit immediately. You don't have to program any of it. Okay, so this is very widely used these days. Okay, and if you ever heard about these solvers like Cplex or Gurobi or Nitro or one of these things, that's model-based optimization. Those are the off-the-shelf solvers. So let's move ahead to I'll skip this last comment here in the interest of time and just move ahead here. Let's move to the next question. How should you do model-based optimization? And this one I can do pretty quick. How do you tell the solver? I've got the problem there, and I've got the off-the-shelf solver. But how's the off-the-shelf solver going to know what my problem was? I just wrote it down in math. It can't read my slides. So how do I translate? I have a modeler's form and I have a solver's form. They're very different. I have my mathematical form. The solver just wants some data structures. And again, there are two approaches, which are for historical reasons called matrix generators and modeling languages. And the matrix generator approach says, use a general purpose programming language to write a program. It'll read the data and it'll build a representation of the solver's data structures according to what you wanted your model to be. And it'll send that to the solver and retrieve the results and do some processing. So you sort of express your model as a program that builds a problem data structure. And by comparison, the modeling language approach is that you take your modeler's form, your form, and you write it in a form that computers can understand. So you just use a language that the computers can read, but that expresses your form, your algebra, the form I showed before. Okay, and then now the modeling language system can read that form. You've just transcribed it to a computer readable version. It can read it, translate it to the solver's form. You don't have to do that. Invoke the solver and present and process the results. Okay? Now, by now, the modeling language approach has pretty much taken over this sort of thing. Okay, so matrix generators are only used really when you're really needing to do frequent fast solves of fixed problems, and you really just want to get everything as fast as possible. But for just about anything else, okay, modeling languages are what people use, and they let people communicate the way they like. It keeps the model debugging separate from the program debugging. It facilitates documentation and maintenance of your things when somebody new comes in and takes it over. They don't have some program to learn, and it structures the whole optimization process. So this one is not such a, there's not much doubt, I think, the direction it's gone. And so now that I've gotten to this point, I can go back and say a bit more about my history. After I worked on that modern approach paper, I got interested in this research and it was clear if I wanted to do this research, I needed to go off and get a higher degree. So I went off to Stanford, and my advisor there was the other author on that paper, George Danzig. Okay. So he supervised my thesis at Stanford with this title. It was more of a algorithm paper, okay, and was involved with that simplex method. That was what they made practical in that paper, okay. And after I got my degree, I got this position at Northwestern, and then I started thinking, well, I still had this report I had written on the modern approach, and I should pursue that further. So eventually that led to an actual published paper, which was also called Modeling Languages versus Matrix Generators, just like that slide a couple of slides ago. Okay? And this described basically what I just told you in a few slides, but in a lot of detail, because this whole thing was much more controversial back then than it is now. And it wasn't so clear to people that modeling languages were actually practical at the time. Okay? But my work at that research center had another effect on my involvement with modeling languages. One of the people I got to know there was a postdoc named David Gay, who was also an optimization algorithm expert. And after I'd been at Northwestern for 5 years or so, I was off at a conference, and I ran into Dave, and I mentioned that, well, I was actually getting close to having a sabbatical coming up. And it turned out he had moved on to Bell Laboratories in the computer science department, a place where they invented Unix or Linux and the C and C++ programming languages. They had a lot of well-known people there. And he said, well, we could probably arrange for you to come and spend a year. And when I went out there to make arrangements, they asked me to give a talk, and I brought this paper along. And the head of my department there hooked us up with Brian Kernahan, who's well known for writing some of the basic books on programming in the C language and stuff. And the three of us decided we would do a new modeling language that was better than what had been done before, and there were sort of use all the ideas that were in these papers, and so that became the AMPL language. Okay, and this eventually was the first paper where we described this new language, and so that job led to a number of things, and eventually we wanted to get this language out into the world, and it turned out at Bell Laboratories at the time the best way to do that was to write a book, and then you could put a disk in the back of the book, and people could try out your software. So we eventually wrote this AMPL book, and so that was sort of the history of how I got into AMPL, and in about 2002 or something like that, eventually Brian and Dave left Bell Labs, and since no one there was doing AMPL anymore, we managed to get the rights to do AMPL away from them and let them give them to us, and we set up a little company to manage it, and that company is now up to 11 people, and they're currently in 7 time zones, although there was a period of about half a year when there were 9 time zones, and scattered all over the place. So we were already prepared for the pandemic before it even hit. Everyone was really working from home, and a variety of different business roles there. But in a small company, these roles overlap a lot. So people aren't too specialized. Everyone's got to do what needs to be done. And currently, we're looking for someone in marketing and marketing analytics. But periodically, we have positions for different things. And so I'll say later the kinds of problems that our customers do when I talk about case studies. But for now, I just want to move on. And before I go on to the third modeling, not programming topic, I want to say something. I just want to show that you can write all this in AMPL. So instead of having written it like this, you see there are 2 sets and some parameters and some more numbers here. And I defined some other set. I can write that in AMPL, and there are 2 sets and some parameters called type, and there's some numbers here. And there's another set of types in each category. So it's the same Same things. And it goes like that. If I have here 3 kinds of variables and 2 kinds of constraints, then in AMPL, I have 3 kinds of variables and subject twos are constraints. I have 2 kinds of constraints. And you can see if this is the constraint and it says for each J and 1, the number of groups and K and C and so forth, you see there's a constraint for each J and K and L. And if it says that this here, this max is greater or equal to that, here you see this max is greater or equal to that sum. It's the same thing. So the idea is that AMPL is supposed to parallel what you write in algebra. And similarly for these others. So these are just more slides showing the same thing. Here's an objective and 2 constraints. Here's an objective to minimize this thing. And here's the 2 constraints, okay, that are the same. And then there are these other ones for the number of women in each group, and I can also write them. But in the interest of time, I won't spend a lot of time explaining that. But the whole thing just transforms into AMPL. And now I can give it to a computer program. It can be translated along with some data and go to a solver. So here's some data, lots of people. I had to make them anonymous. And here's 3 or 4 categories. Here's a big table that tells you for each person what all the categories they're in. And number of groups has to be, there are 12 groups between 16 and 19 people. And now I can read the model and the data and send it to a solver. I send it to CPLEX. Well, in less than 6 seconds these days, it sends me back an objective. Okay. And you can check 16 is pretty good for this because the number of types is around 16. And if I don't want to use CPLEX, well, I can use Gurobi instead. So with a modeling language like this, you can switch to whatever solver works best for you. And solvers come a long way. This has become like an easy problem. And I threw in all the isolation constraints here, not just the ones I showed you. And so now I can finish up with the third modeling, not programming topic, which is what kind of modeling language. Okay. And well, you want to choose a form that's used by modelers and design a computer readable version of it. There are all sorts of specialized forms used by modelers, but the kind of modeling language that's most used is this general form based on algebraic notation, which is just what I showed in all my math examples. Okay. So AMPL is an algebraic modeling language, and that's mainly what I'm going to talk about. There are 2 popular approaches to algebraic modeling languages, which are called declarative and executable. And again, it's a question of programming or not programming. So the declarative approach, which is like AMPL, is you design a new independent modeling language for describing mathematical models. And the idea is to make it as similar to those models as possible. Okay? And then when you want to embed a model, eventually you get your model working properly and you want to embed it in some larger application, then you have some facility for writing little scripts or little sort of AMPL programs. So you have a few things in AMPL that have, there are a few little loops and so forth that really aren't part of the modeling language, but that work with it. And then or if you want, there are APIs. So if you want to call the AMPL model and everything from C++ or Python or R or whatever you like, then you can use the API and embed it in some bigger application that's in Python or whatever. Okay? And you get the advantages of AMPL for modeling and the advantages of Python or whatever for application building. Okay? And the other approach is what I call, well, here's an example, okay, of really simple example of an AMPL model, which I just want to put there. You know, it's got variables, minimize, subject to this, subject to that. Now, how does that compare to the executable language? Well, there the idea is start with a programming language and make it look more like a modeling language. Create an algebraic modeling language inside your programming language, okay? And use some general purpose language that's popular, okay? So here's an example in Python. So this is actually that same model that I showed you, but in a Python modeling language. So let me compare them here. And you see, for example, I have 2 kinds of constraints here. I have 2 kinds of constraints here. This one says the sum of the flows less or equal to the capacities. Well, this also sort of says the sum of the flows less or equal to the capacities. This one says for each arc. This one says for each arc, for each ij and arcs. Okay, you can do the same with this one. And I've sort of the objective's been embedded in here, but you can see that the variables are defined by some add vars method. The constraints are defined by some add constraints method. So it's taken sort of Python-like things and made them look like a modeling language, okay? And to hopefully make it easier to express models. Right? It's not perfect, and you can get into situations where you've got some, you're not sure whether you have a modeling bug or a programming bug. All you know is that your model's not working. But among programmers, it's become quite a popular alternative. So that's the other alternative. So what are the advantages? Well, the executable languages, the big thing they say is you can develop your whole application in one language. Use all the benefits of C++ or Python or whatever, and get streamlined deployment of your whole application. And it gives somewhat tighter integration with solvers. On the other hand, the declarative modeling languages like AMPL make your modeling independent of the programming. They don't get it stuck in Python or something. And they're really designed for an analyst who wants to focus on the modeling and not worry about how to make it fit in immediately in the whole application. And they're focused on getting the model developed quickly. So one of the big problems with any optimization project is to get some results before your department loses interest entirely. And to do that, you want it to be something that makes it easier to get the model developed. And something like AMPL that's designed for writing models makes it easier to do that than something that's written in Python or C++, where you have to worry about how to get the programming right. Okay, and also the model translator in a declarative modeling language was designed to translate models quickly. It knows a lot about models, whereas the compiler that you run the Python program through doesn't really know that you're doing modeling. And there are all sorts of special things you typically need to put in to make sure that your sums remain efficient when they get really large. And so in that Python example, that language actually has 3 or 4 different ways to write sums, depending on how big they are and how different they are. Okay. So then I'm going to finish up here by concentrating on AMPL and saying some things about the range of AMPL users and showing 3 case studies that'll give you an idea of what happens. There are AMPL users in just about anything. Since it's a general purpose modeling language, you can use it for models and all sorts of things. There are a great many energy applications, like largest number in power flow, but there are ones in just about anything that has to do with energy. And all sorts of industries. Okay. Transportation is a big thing, any sort of distribution, scheduling of deliveries and so forth, various kinds of services, communications, finance is a big application. There are really big users in finance. And what do they do with AMPL in finance? I can't tell you, top secret. But all we know is they keep ordering more of it. And it's well known that there are things like portfolio building tools that can be done by optimization. But what they really do these days, they don't want the competition to know. And then various advanced technologies as well use it. So the general purpose nature of it really pays off. It hasn't really settled down into just one niche. Okay, so I'm going to describe 3 very different applications here, and each case study will have 3 slides, and there'll be one that sets up the problem, and one that says how they decided to use AMPL, and one that says how they implemented it. Okay, so the first one is an application in Dropbox, which you may have heard of, and so Dropbox, is a cloud system, and it's for storing your files in the cloud. And but what Dropbox is interested in for this application is not people like us who store a bunch of things. What they're interested in is big corporate customers. They have corporate accounts where they've supplied Dropbox for everyone in the company. And for those, they have sales reps assigned to them to keep them happy. And so among these 500 million users, what they want to concentrate on is the tens of thousands of large business customer accounts. They have hundreds of sales reps who can cover most of these accounts. And their problem, not surprisingly, is to assign accounts to representatives. So here's another assignment problem. Okay? And they want each representative to get a similar number and quality of accounts. So it's not just assigning them, but they want everyone to get sort of a fair distribution of accounts. And if they can't assign all of them, they want the higher quality of counts, which they define somehow to be assigned. So how did they make evaluation of this? Well, they considered a manual system, something based on spreadsheet solvers, and an automated system that used model-based optimization, which is what they chose. Okay? And they chose AMPL because it was easy to use and fast. They got reliable results because they could see the model and see whether it was doing what they wanted, and it could handle large problems for them. And so to implement it, 3 analysts at Dropbox did this implementation. So it all required is people who could understand how optimization models worked. So, and they used a mixed integer linear solver. It has about 10,000 0-1 variables like those XIJs I showed. And for the largest region they solved, it actually took 3 to 6 hours sometimes. Okay, but they didn't have to run it very often. So they weren't too concerned if it took a long time. And so direct users are 5 to 10 sales leaders in different places who run this thing. And they embedded it in their system. So the customer data was extracted from Salesforce, which is, and then their scores were computed learning using a Python toolkit. So that computed a score of how useful the customer was or how valuable they were. And then they fed that all in using an AMPL script to read in all the data. And then the results to the optimization were written to a spreadsheet that was then disseminated to people to tell them who they'd been assigned to. So they brought together a lot of software here, which is really typical. It's very rare that someone just runs optimization in a big company, all as a standalone system. It's usually connected to other stuff. So that's the first example. The second one is an outfit called Young's Plant Farm in Auburn, Alabama. And this is more of a supply chain problem. And this is a huge plant grower. And they ship to, when they grow these plants, they then ship them to retailers on their own fleet of trucks. And their customers are really large. They include like Walmart and Lowe's and companies like that for each store sell huge amounts of stuff, make really big orders very frequently. And now their plants are packed on these special rolling racks. Here's a picture of one. And so somebody drives this tractor around with this rack and goes and picks off the plants that are needed for a given customer. And then they ship the whole racks to these customers. Okay? So they have to decide what should be picked for what rack and so forth. So what they need is a good packing plan for a whole day's orders. Okay, they've got some orders there and they've got the racks and they've got to decide what to put where in every rack so that then they can load them quickly into the trucks in time to get the orders out. Okay? It's not the sort of thing you can do in your head. Okay? So what did they consider? Well, they considered doing it by a spreadsheet and having somebody the previous night move everything around the spreadsheet till they got what they wanted. But what they chose was to use instead of modeling language, AMPL in particular, and one of these solvers. Okay? And they found that using a real model and a solver like this gave them dramatically better solutions and actually faster solutions using fewer people, and that loaded the racks faster and required fewer trucks. So really optimization just paid off there. And also it gave them a selection of solvers. So they could decide what the best solver was after they had developed everything. And they weren't tied down. There were like 3 really good solvers for these kinds of problems. But the one that works best for your problem is hard to predict. Okay? And how did they implement it? Well, here's an example. This was originally built by a professor at the local university. So Auburn University is in Auburn, Alabama. It's really the state engineering school. And so he did it originally, and then they eventually took it over. And when they got to some really hard stuff, actually one of our developers helped them out as to how to do really large orders and what the tricks were. He had some experience with that in his thesis work. So they now do really large things. A big barrier for them was how could they get Walmart in there because they were so big. Okay? And so it's implemented using AMPL model data and script. So no API in this case. They just use they just do the programming even in AMPL to implement it and or to embed it in an application. And they run from hundreds of thousands of variables to 100 million variables. Solve time is 10 to 45 minutes. So they're really pushing this thing here. And but this is what they need to do to deploy it. And to deploy it, then they have a special spreadsheet, okay, which does the data prep and the result reporting. So basically, there's a spreadsheet out there that they use to get the data in, all the data ready to make the decisions for the next day. And then they run some spreadsheet scripts that send out the data ready for AMPL. Then they run the AMPL stuff. They run some AMPL script that does all this, gets the solution, and it sends a report back into the spreadsheet. And then they got some more things to do that, some more routines that they do to deploy that. And so one specialist uses this tool several times a day to get the rack scheduled. And they're already looking at new adaptations of this. So I think it's a pretty good, typical, good supply chain example. And like most supply chain examples, it wasn't just a matter of modeling it and then going to, at some point they had to get over a hump, like the size of the Walmart orders, and they had to change some of what they did. But once they got going, they saw the advantages of it. And so they pressed ahead and really had a lot of success. And then the third one I'm going to show is this company called ABB, which is a power company. So remember I mentioned that power transmission is a big application. Okay, and here AMPL is built into a product they have called GridView. Okay, and GridView is essentially something that makes decisions about how to manage your power grid. And two kinds of decisions. One is you'd expect is network flow. How much power should flow out over various lines to various places? And the other is called unit commitment, which is when to turn different plants on and off to accommodate the swings in the amount of power demanded. And GridView is not actually used on a day-to-day basis. It's used to simulate optimal decisions to support planning of the network, to decide when to do expansions, when to add or retire plants, or expand the transmission network, or integrate new energy sources. So the idea is to say, if we did this, how would the system behave? Would it be adequate? What problems would we run into? Okay. And so they sell this to energy operators. Okay. They consider doing the whole thing in C++, but the approach they adopted was to use C++ for all their interfaces and of the GridView product, and to use a modeling language for the optimization. And they chose AMPL because the modeling was easier. They could formulate these complex and powerful models, and they could actually show them to their customers. And customers could even ask for specializations for particular situations. And this is not something they could have done if it was in the C++. You can't show C++ programs to customers and expect them to understand what the model is doing. And even if it's a modeling language in C++. And then they used AMPL C++ API to build AMPL into the GridView product. And then how did they deploy it? Well, again, this involved the university. The prototype was done at University of Tennessee at Knoxville, and you won't be surprised to know that this branch of ABB is in Knoxville. Okay, so they went to the local university and asked, and eventually 3 analysts at ABB took this over. And of course, they have quite a few technically savvy analysts. So they took this thing over and built out the whole GridView thing. And it has a mixed integer linear solver. There are millions of variables, tens of thousands of them have to take integer values, but this problem solves in 10 minutes. Okay? So it doesn't take long to run scenarios. Okay? And there are 30 plus customer companies with hundreds of customer side users using this thing. Okay? So that's just an example of the kinds of things we do. And you see that the people on the customer side we rely on them to do a lot of model building. And what we try to do is provide packages that have everything they need in order to do that. Okay? So thanks for your attention. That brings me to the end of the presentation here. And I'd be happy to answer questions.
Okay, thank you, Doug, for your enlightening speech. I really enjoyed the lecture you gave tonight, and let me give a brief summary first. So you started from the definition of optimization and how has your title, modeling, not programming, the modern approach to optimization in operations research come from, and you explained the profound things in a simple way. So you told us how did you start to invent the AMPL language and how to create an optimization modeling language, and introduced a few applications. So do you have any questions? So if you have questions, you can ask at any time.
Yeah. Don't be afraid to speak up.
Yes.
I'm sorry, I entered this meeting late, but I only caught the last 15 minutes of the applications of AMPL. But I'm wondering, like, how can I get my hands on this? I've used Lingo and other kind of software to handle such optimization problems, especially like, you know, integer programming. But like, how can I get my hands on AMPL?
Okay. So let me, in fact, show you the screen here. Where is, hold on a second. I need to, oh, I see. There we go. I'll show you here, just where you should look. I go here, I go, no, this is it. Okay, so now we can go here and I can share this thing, and now I can share this, and so here's the AMPL page here. And now if you go here to try AMPL, okay, it'll give you a variety of ways to try AMPL, and one of them is you can get a free demo just by downloading from this page. A bunch of instructions here, okay, and but that demo is size limited. But if you just want to try it out to see how it works, you can follow the instructions there. If you want to get a full-featured version, there are a number of possibilities, and one of them is you can request a full trial. And in fact, you can go to our AMPL for Students page here, and here's a video introducing it. And there's a form down here. You fill out this form, and we send you a 30-day trial with full versions of all the solvers. And there's another thing here, which is mentioned that yeah, when you're getting your graduation, you can get this free AMPL for new graduates as well, which is good for a year, and it's unlimited in everything. And if you're going off to work somewhere, you can take it with you. And so that's a number of things. There's one other thing you can do. There's something called the Neo server, and so there's actually there's this free site that has like I have 40 solvers and connects to several modeling languages, and you can send models and data to it, and it'll send you back solutions. It'll solve quite large problems, and it's completely free. And it includes all the solvers that you've heard of. So, you know, Gurobi, Cplex Express, Nitro, etc. And all these ones you haven't heard of are on there. So it's another option if you just want to try a bunch of things. And so there are quite a few ways to get started. And all you have to do is go look at these try AMPL things here on the site, and you'll see it. And the demo you can download right away. So, oh, one thing more I should say, there's a whole AMPL book that I showed, and you can download chapters of the AMPL book, and you can just start off with those. So if you want to know how's it work, how do you get started on it, this is all entirely tutorial. It's not like a dry reference manual. It has examples. It works through all the possibilities and so forth, and it remains tutorial through the whole book. So So you can go through as much as you want to see how it works. Okay,
Awesome. Thank you.
right. Let's see here. Let me, oh, I see, stop share. Okay. Okay, other questions?
So I have a question.
Yeah.
You mentioned model-based versus method-based optimization.
Yeah.
And obviously AMPL is a model-based optimization.
Yeah.
So you mentioned that for large intensive application problems, we might be using method-based optimization. Is it because that model-based optimization is good at find the optimal solution, and method-based is good to find a good solution, but not optimal. But if we are satisfied with the good solution that don't have to be optimal, we'll use method-based for large applications.
Well, not exactly. I'd say that so when you present method-based optimization, you always talk about these optimization models and always says maximize this, minimize that. But if you look at how people really do things in practice, they use these solvers as heuristics. They don't like in fact, you take a solver like Cplex or Gurobi that's supposed to be optimizing, and you look at, by default, it stops when it can prove that the solution it has is within 0.01% of optimal. It doesn't even try to prove complete optimality. And many people set that to 0.2%. And they say, oh, that'll be good enough if we can just get to something there. And then there are also, there's another whole talk I've given on this topic, that when you have a really hard problem, model-based optimization is still useful, but you may have to cheat on the solution. So what you do is you make up a model that's not actually guaranteed to give you the very best solution for the whole thing, but with very great likelihood, it's going to give you a really good solution. And so a lot of the, models are only models. So actually, even people who build models and run them to optimality are only getting optimality of the model. And often that's an approximation to reality. So I don't think there's a complete division between method-based things for approximation and models for exact optimality. I'd say that models, I'd say that there's sort of some overlap between them. And the overlap has gotten greater and greater with time. And there's even sort of hybrids where people, they write a method, but what the method does is it through the method. So it's a method that is built on top of models. So that too. Why is it doing this? I don't know if you can hear me, but it seems to be.
Yes, we can hear you, but
Okay,
your
yeah,
image just
okay. Yeah, Zoom
stopped.
is doing something weird. But if you can hear me, I'll just say that it's possible to have. So things are not as simple as they used to be.
Yeah, thank you for your answer.
Okay.
So any more questions?
Okay.
Hi, so I have one question. When we solve a problem like utilizing Excel solver, so we later on can add constraints to, let's say we want to optimize it on a different scenario. So we add constraints later on or change some things to make it integer-based solution, or to change it to a particular whatever integer we want. Can we do that in AMPL as well?
Yes. So you can add constraints. You can change constraints. Or for example, the most often thing is that the constraint is indexed over some sets of signs, and you can keep changing the sets. Or you can actually drop and add different classes of constraints. So so that's not unusual.
Okay. And if we have like data in Excel or in CSV format, then can we import that in AMPL?
Yes, yes. So there's a specific facility for importing from Excel or CSV, and you basically you tell AMPL what the tables in the spreadsheet look like, and which columns in the table correspond to which data in AMPL. And then when you're ready, you just say, okay, read it now, and it reads it. And there's a corresponding thing for writing the data back out to the spreadsheet. So that's a widely used sort of feature. Okay.
Hi, Professor. I have a question.
Yeah.
I really like the talk. So in some of the optimization problem that I am currently solving, one aspect that I miss in AMPL, but available in other languages like the built-in or user-defined methods or function. Is there any feature available that in AMPL, or is there any plan to add it?
Yeah. There are user-defined functions. They have to be written as C functions. So I would like to add, we are talking about adding like Python functions, but right now there is a way of adding a C function that would be like that it'll call when needed. So it's the biggest use that you want to have your own functions, I think, is if somehow they're functions of variables that figure in your model. Okay.
Yeah.
Right. And they're not functions that are standard. So we have this tied to this big library of standard functions. And that's not a problem. But if you have some special function that's special to your application, and it's a function of variables, then I think that's where you'd want this sort of thing. Other kinds of functions that are just functions of data you can do outside of AMPL. So and use the APIs.
Okay, thank you.
Yeah. Okay.
Okay, so if we have no more questions, then it's the end of the event today. And I want to appreciate Dr. for again for giving the lecture today. And yeah, and okay, so he maybe have some network lag. So and it's the end of the event. Thank you everyone for joining us. Okay, see you. Have a good night.